Kia ora, Year 12 and 13. This is the second video on optimisation. This is another classic problem, and you'll see lots of variations on this one in different books. If you want more practice, you can just change the numbers around for yourself once you've been through this one. So this box is made out of shiny cardboard, and the cardboard comes in two types. There's expensive stuff, and that costs $20 per square metre. Right? And then there's the cheap stuff, and that costs $5 per square metre. Now you decide the top and bottom of the box should look lovely, so you'll use the expensive stuff there, and that should say the top, not the two, and you'll use the cheap stuff on the sides. The volume of the box has to be 70 cubic metres, and the base has to be 3 times as long as the width. So your mission is to minimise the cost. Okay, so we're not trying to maximise the volume, we've been told the volume, and that needs to be 70 metres cubed. So that will be one of my constraints here. Okay, so if you want to give that a go, start by sketching the cardboard box and writing down as much as you can from that question. Okay, so the first thing to do is to draw something resembling the cardboard box. Alright, and then write some statements down. So we'll have L is the length, W is the width, and H is the height. Right, and we can write down that V is equal to length times width times height, and that equals 70 metres cubed. Now the next thing we want to work with is the cost function. So what is this cardboard box going to cost? So we might do some nice colours here. Let's do blue for the top and the bottom. So there's the blue expensive cardboard, right? And you'll just have to imagine that. Oh no, I'll try and draw it in, right? So people in my class are used to the bad pictures, but there you go. So that's the expensive stuff. And then on the sides, where we'll do the cheap stuff can be pale pink. Okay, so the cheap shoddy stuff is going to be that colour. So there will be 4 sides, right? So matching, oh what a mess. So 4 sides that will have the cheap stuff. So we're going to write down the cost function now. And we'll call that C. So C is going to equal the expensive stuff for the top and the bottom, so that's $20 times 2 for the top and the bottom, times the length times the width, plus the sides. Well, 2 of the sides will have dimensions HW, so it's going to be $5 times 2 times HW, and then the other 2 sides are going to be these ones here, so the kind of the front and the back face, right? They're also going to be cheap, and they will have dimensions length times height. Okay, so you might be suspecting that you might be going to end up with quite a tall box, so the height might be a bit bigger. So if you can get some kind of intuition for the shape, that's a good thing, right? And then the last thing we've got, the last constraint that's also going to help us, is that the length must equal 3 times the width, right? So what we've got to do is put those things together. We've got the volume, LWH is 70, and we've got the length is equal to 3 times the width, and we're trying to minimise this cost function. So our strategy has to be, as in the simple problem of the farmer in the paddock, to try to eliminate some of those variables, because we're going to want to differentiate the cost function, and to do that we need to just have one variable. So you can have a go at doing that now. So pause the video, and I'm going to go through how we do that on the next slide. Okay, so we've got C is equal to 40 LW plus I'll take out the dollar signs actually, they're a bit silly now. So, whoops, let's erase it. There we go. So C is equal to 40 LW plus, no more dollar sign, what have we got? 10 WH plus 10 HL, right? And I'll make that L like that, just to make it a bit cleaner, right? Now, what do we know? Well, we know that L is equal to 3W. So the first step is to get rid of the L's. So C is equal to 40 times 3W times W plus 10 WH plus 10 H times 3W. So we'll clean that up first. We're going to get 120 W squared plus, well, I've got 10 WH here and I've got another 30 here. So I've got 40 WH. So the last thing I have to do is to get rid of the H. Now the thing I haven't used yet is this fact here, that 70 is the volume of the box. So 70 is equal to LWH, which is equal to 3W times WH. So 70 equals 3W squared H. So I can use that expression to make H the subject and then eliminate the H terms. Okay, so try that now. Right, so we're going to get H is equal to 70 over 3W squared. So we had got to here on my cost function. We had 40 times 3W squared plus 40 WH. So that equals 120 W squared plus 40 W times 70 over 3W squared. So I think I did say at the start that this was a little bit of a step up from the farmer in the paddock. So just, if you're finding this a bit full on, just pause it and go back over what we've done so far. That's 2800 over W. Right, so this is starting to look pretty doable. Okay, this is my cost function and I want to minimize it. I've got it to a form where it's just got one variable in it. So now to minimize, I'm going to differentiate and set the first derivative equal to 0. Right, so C is 120W squared plus 2800 over 3W to the power of negative 1. So C dash of x will be 240W minus 2800 over 3W to the minus 2. So for a minimum, we need the first derivative to be equal to 0. So we're solving 240W equals 2800 over 3W squared. Right, so I'm setting that expression equal to 0. Okay. Now multiplying both sides through by 3W squared, I get 720 W cubed equals 2800. W cubed equals, well, let's have a wee look. Okay, I know you can do this on your calculator, but I'm not. So we have 2800 over 720, right, which is equal to 70 over 18, right, knocking out doing some easy simplifying there, which is 35 over 9. So the width is equal to the cube root of 35 over 9. Right, see if you can get to the end from here. So pause it now and keep on going, do some back substitutions. Right, so it's worth evaluating that cube root now. So W equals, and I'm going to write this out with lots of decimal places here. I definitely want to round that up, but I don't want to do it till the end or I'll lose accuracy. So W is equal to 1.57, blah, blah, blah. The length is equal to 3 times the width, so that works out to be 4.717694 metres. Lastly, the height will be equal to 70 over 3w squared, and that works out to be 9.435388 metres. So now I want to round those, but I don't want to do the rounding until I've figured out those two there. Okay. Right, so we've got the cost overall of the cardboard box. Go back to that expression, and if I substitute in W equals 1.572565, I will get the cost is equal to $593.51. Okay, now I need to also give the dimensions. So the width is equal to 1.57 metres. The height is equal to, the height is equal to 9.44 metres. It's quite a strange looking cardboard box. And the length is equal to 4.72 metres. But there's one thing that I haven't done. I haven't checked to make sure that I have found a minimum. So that's the last thing that I want to do. Right, so we had C of x, C of width. So the cost as a function of the width was this. Right, and we got the first derivative. And the first derivative was 240w minus 2800 over 3w to the negative 2. Now we have to work out the second derivative, and for a minimum we want to check that it is positive. So it's 240 plus 2800 over 3 w to the negative 3. Right, and we can see that that is greater than 0 because we've got a positive value of w. Okay, so we've found that the second derivative is greater than 0. So second derivative evaluated at, what was our w? At 1.57 is greater than 0. So we have found, and we had the first derivative, of course, was equal to 0. So we have found the local minimum here. Right, so we've found the dimensions of the cardboard box, and we've also found the cost. Alright, that's all for now. There'll be another optimisation video coming soon. Thanks for watching.